Right. Okay. So it's my great pleasure to have Stelzer from UIUC to talk about Grothendieck polynomials, Hilbert series, and so on and so forth. Take it.
Great. Thank you so much. Yeah. So I believe this is a symmetric function friendly crowd, but just to make sure that we have some common terminology, I'm going to be talking about Schur polynomials a lot today, and so I'll define one through an example. A Schur polynomial is the weight generating series for semi-standard Young tableau of a partition shape lambda in some collection of variables, T1, in this case, T1 through T3. I draw my partitions in English notation. Sorry if you prefer some other notation. So this is the partition T1. And in this case, it's not too hard to just write out all the semi-standard Young tableau. Sorry. There's 8 of them. So, you know. Okay. So, right, we've got 1, 1, 2. Watch me mess up. Let's see how it goes. 1, 1, 3, 1, 2, 3, 1, 3, 2, 1, 3, 3, 2, 2, 3, and 2, 3, 3. Okay. So yeah, well, I am going to use x's later, but I want to be a little bit careful with my choices of variables to avoid confusion. I'm using the indices of the variables. I guess maybe I should be writing T1, T2, T3, but I'm just going to write the numbers. Yeah. And so to each of these tableaux, we can associate a monomial weight by recording the number of 1s and the number of 2s and so on as a monomial. So in this case, our monomial is going to be T1 squared T2. For this one, it's T1 T2 squared. Then we've got T1 squared T3. Here we have 2 different tableaux with the same weight. So we're going to have plus 2 T1 T2 T3. And then T1 T3 squared. T3 squared. T2 squared T3. And finally, T2, T3 squared. And you can see that this is a symmetric polynomial. If I swap around any 2 variables, I'm going to get the same thing. And these, in fact, form a vector space basis for the vector space of symmetric polynomials. And they also are interesting symmetric polynomials, right? They're the characters of irreducible GL representations, and they show up in Schubert calculus and lots of other places as well. Okay, so they satisfy a number of interesting identities. Here's one of my favorite ones, or 2 of my favorite ones, really. The Cauchy identity and the dual Cauchy identity. So just write these down. So this is the Cauchy identity, and then I'll write down the dual Cauchy identity as well. Okay, so these are 2 wonderful classical identities about Schur polynomials. So over here, we see this condition in the sum is actually superfluous. If I took lambda, the length of lambda here just means the number of rows in its Young diagram. And if I made this bigger than m or n, then there would be no semi-standard Young tableau using numbers from 1 to m or numbers from 1 to n. And so these Schur polynomials would just be 0. So I don't really have to write this in, but I think it's helpful. And then we see that that's equal to this rational function over here. And then similarly here, if we take lambda, whose Young diagram fits inside of an m by n rectangle, and we take this product of symmetric polynomials, if I write vector x and vector y, that's always going to be x1 to xm and y1 to yn. I just don't want to write it out every time. And here, this apostrophe means that I'm looking at the conjugate of lambda, which I get by transposing its Young diagram. And so if we take this product, this sum of products of Schur polynomials, then we get this thing, which looks very similar. And so these identities have representation theoretic interpretations using symmetric and exterior algebras and such. But they also have very nice combinatorial proofs. This left-hand side here in the classical Cauchy identity is, by definition, the weight-generating series for pairs of semi-standard Young tableau of the same shape lambda, where one partition is filled with numbers from 1 to m, and the other one uses numbers from 1 to n. And the right-hand side, if we take each of these factors expanded as a geometric series, and then take the product and distribute through, we'll see that this is the generating series for m by n non-negative integer matrices. And so to prove this identity, we just need to find a bijection between those two sets, and that's what the Robinson-Shenstedt-Knuth correspondence does, which is central to a lot of algebraic combinatorics. Similarly, over here, this is, by definition, a weight-generating series for certain pairs of semi-standard Young tableau. And if we multiply this out, it's the weight-generating series for m by n binary matrices. And there's a dual RSK correspondence that once again gives a bijection and proves the theorem. Okay, so what I really want to talk about today is a common generalization of these two identities, which I think is very beautiful. Let's get it written down here. So for all k between 0 and the minimum of m and n, we have this identity. Okay, long formula. I'm curious, show of hands, has anyone seen this formula before? Yay, okay, found something new to show. There's some notation in here that's undefined, so I should quick define that for you. So I'll define it through example. Let's take lambda to be my favorite partition, which is 4, 2, 1. So this partition has a statistic associated to it, which is sometimes called its rank. The rank is the side length of the Durfee square, which is the largest square contained in its Young diagram. So this partition has rank 2. And then the k stabilization of lambda, I'll write down maybe the 3 stabilization here, is another partition that you get using the rank of lambda is lambda. I write sub 3 in parentheses, and I get it by taking my partition and adding 3 rows to it, each of length equal to the rank. So in this case, add 3 rows of length 2 here, and then we have our 1 at the bottom. Right, so kind of a weird operation, but certainly well defined. And then over here, we have this beautiful identity where you'll notice the left-hand side is very similar to the left-hand side of our classical Cauchy identity. The only difference is that instead of the trivial condition that lambda has at most minimum of m and n parts, we have some more substantive condition depending on k. And then the right-hand side here, we can see actually if k equals the minimum of m and n, then in this numerator, we're summing over lambda that fit in a 0 by something rectangle. So the only lambda that does that is the empty partition, and this numerator will just be 1. And then we will recover the classical Cauchy identity. On the other hand, if we take k equal to 0, then in this sum, the only partition with at most 0 rows is the empty partition. So this side is 1. Over here, we're looking at lambda inside of an m by n rectangle and the 0 stabilization. So it's just lambda and its conjugate. And if we multiply across by the denominator, we will get the dual Cauchy identity just with a substitution like yj goes to negative yj, which doesn't change anything. So this is like an interpolation of, or a generalization of, both the Cauchy identity and the dual Cauchy identity. And now I can tell you an open problem. Let's call this identity. Yeah, of course.
If I was to take this denominator to the left-hand side and start in the first Cauchy identity.
Yeah.
So this thing is signed, right? Signed multiplicity free, the numerator.
Yeah.
So can you do everything combinatorially? Like, can I do like a RSK,
Yeah.
two RSKs together to?
Yeah. So you exactly anticipate my problem. No, which is give a direct proof. Of this formula for all k. And so, of course, when k is 0 or the minimum of m and n, then you can do that through RSK or dual RSK. In general, you can either take this denominator and expand it using this, or you could multiply across and then use the dual Cauchy identity on this expression to get it in terms of Schur's, and then use Littlewood-Richardson rule or whatever you like. And you'll get some big, crazy alternating sums that must cancel out to give you something nice. But I don't know how to do that. I'm not aware of any proof of this. Except in one case. So working this summer with an undergraduate, Liam Butita, we were able to do the case where k equals 1. By basically doing that, like just expanding out and understanding the cancellation and seeing what you get. But for the other cases, I feel like if k is equal to the minimum of m and n minus 1, it's probably also tractable. In general, we're trying to do it for general k, but it seems hard. Not exactly assignment reversing involution. What we did was, so we took this, multiplied across, applied the dual Cauchy identity, then you multiplied through here, and because these are partitions with at most 1 row, you're just doing the Peary rule as opposed to the Cauchy identity, and then it turned out that like you get an alternating sum, but they're always alternating sums of like binomial sequences. And so then it's easy to see that they always cancel and give you 0 unless it's like the binomial sequence that's just a single 1, which exactly corresponds to these cases. Yeah, so we didn't like explicitly do a sign reversing involution, but that's basically the idea.
If I was to do a principal specialization, like both x's and y's set x of I q to the I minus 1, then when you get like a hook content q hook length formula, even in the case k equals 1, if I was to do a principal specialization, you get like squares of q binomial coefficients on the left hand side. You get a fairly nice expression of the denominator with like plane partitions and stuff. Okay,
yeah, no idea. Yeah, no idea what you get if you do that, but yeah. Okay, so I think this formula basically, if the only thing you take away from this talk is that this formula exists, then I consider that a big win because I love this thing and I would love more people to think about it. But the question stands. So if we don't have a direct proof for it, how, as combinatorialists, would we know that this is true?
So where's the notion of case stabilization? Like where did you, I've never seen this before as far as partition theory.
Yeah.
Who is this due to?
Well, so ultimately it will be due to a formula of Lascaux that I'll get to a little later. But it comes, I'm not sure, like I haven't seen people use this notation other than me when I talk about this. But why this operation ends up being the thing ultimately comes down to the Borel-Weber theorem when you write it algorithmically. You'll see this sort of thing start popping out. You can also understand it if you were to write. So this is going to come from some representation theory stuff. And if you think about rational representations instead of polynomial representations, then you're sort of, you can understand the stabilization as taking a rational partition that has a bunch of zeros in the middle and just adding more zeros to the middle, which maybe makes it look more natural than this. Any other questions before I move on? All right, great. Nice. I guess I want to save this space. So is it okay if I erase the setup here? Okay. So we want to give a proof of this theorem. It is known. It's not like a conjecture. But to give the proof, we're going to need to talk a little bit about the algebraic geometry and representation theory. So
when you say
This is your theorem, right?
this is
no, I wouldn't say it's my theorem. I would say that I haven't seen people other than me write it down this explicitly, but it's known. In fact, I would say this was maybe known in like the 70s. But it comes from putting together a couple of theorems by other people who mostly didn't write it in this concrete of terms. Yes. Yeah. Yeah, but definitely not like I didn't prove anything to say that that's true. Okay, so suppose now let V be a d-dimensional vector space. And I'm going to think about the right GLV action by V gets acted on by G via G inverse times V. I know that looks slightly wonky, don't worry about it. You know, it's just usual like multiplication action, and the inverse is just a technicality. So I want to think about V as an affine space because I want to do algebraic geometry with it. So we're going to think of this as, you know, a space that has an associated coordinate ring of polynomial functions and like a basis of V. And then we want to think about affine subvarieties or subschemes of that space. Okay. So we have V here, and algebraic geometry tells us that if we want to study V as an affine space, we can equivalently study the polynomial ring that is its coordinate ring. So I guess our technical definition of this is that it is the symmetric algebra on V dual, and concretely that is isomorphic to a polynomial ring and some variables Z1 through ZD. Right. And then suppose we have some oh, there's a question? Question. This is not a group action? Yeah, it is. Why not? It's a right G action. Sorry. Yeah, it is a group action, but it is a right group action. Yeah. So then we have some affine subscheme X. So the solution set to some system of polynomial equations. And that also has a coordinate ring associated to it, which is just going to be the quotient of our polynomial ring by some ideal, which, you know, is the ideal generated by the equations cutting out our subscheme. Right. So if we want to study the geometry of our variety, we can equivalently study the algebra of this thing. The fact that our X is embedded corresponds to the surjection going the other way. This is like the basic conceit of algebraic geometry. And when we think about GL acting on the right on V, we get a left action of GL on the coordinate ring of V. Namely, we have the action, so GLV acts on the coordinate ring V by G times F of Z is equal to F of GZ. So I was just picking the inverse so that when you naturally go through here, you get a left action. That's this nice thing. Okay, great. And if we're lucky and we pick a nice X to work with, our X will also be stable under this GL action. Or later on, maybe we won't take GL, we'll take some nice subgroup of it, like a product of GLs or some other reductive group. Okay. And so then as soon as that happens, you have an action. If you have a GL action on X, then the GL action on the coordinate ring here will descend to a GL action on the coordinate ring here. So if GLV acts on X, then the coordinate ring C adjoin X is a GLV representation. And this is good news for us, because if we want to study varieties, like any geometric properties we want to learn about, if our variety has symmetry represented by some big group action, it's usually productive to try to incorporate that group action into our studying of its geometric properties. And via algebraic geometry, that corresponds to studying this thing as a GL representation. And since the representation theory of the general linear group is very well understood, this can be like a really powerful tool. Okay. Does that general setup make sense? Okay, great. So what's the takeaway here? Well, I said that the GL representation theory is very well understood. We know that the irreducible GL representations are these things called Schur modules, which I'm going to denote V lambda of D, because it's a representation of GLD, where lambda is a partition that has at most D rows. Okay. And so this tells us that our coordinate ring of our variety, because GL is a reductive group, that means that this coordinate ring has to decompose as a direct sum of irreducible GL representations, namely the Schur modules. And so we have to have some expression like this. Sorry, it's getting pushed over to the side here. I'll write it on a new line. We're going to have our coordinate ring here decomposed as a GLV representation into a direct sum over lambda with at most D rows of V lambda D, each occurring with some multiplicity that I'll call C lambda X. And we know that those have to be non-negative integers. Okay. So how do we actually figure out this decomposition? Because, you know, we're combinatorialists. I don't want to try to do like fancy representation theory things. I want to do concrete calculations and stuff that I can code up on a computer, right? And so it turns out, through the magic of what's called character theory, the character of this coordinate ring is some polynomial that is associated to it. And if you know how that character, let's see, let me back up. If this coordinate ring is a GL representation, then the character has to be a symmetric polynomial. And the characters of the irreducible GL representations are Schur polynomials, which form a basis for symmetric polynomials. And so if we express this symmetric polynomial in the basis of Schur polynomials, it turns out that the coefficients in that decomposition are exactly these coefficients that we're looking for. So this tells us that we have an expression here of C lambda X, S lambda T1 up to TD. Okay. Character is the numerator of the Hilbert series. No, not quite. The character is the Hilbert series, which I'll say in a minute. But yeah, I'm not as a fractional thing, not as like a rational function, but just like as an infinite series. The character is the Hilbert series. So let me write this over here. Our takeaway from all this is that if GLV acts on some variety X contained in the affine space V, then we know that the character of C adjoin X is going to be equal to some sum for lambda of C lambda X times the Schur polynomial. Okay. And this makes us happy as algebraic combinatorialists because I've given you some general algebraic setup, and then I've told you that there's some concrete computation that you can do if you just had some way of obtaining this character, which maybe you can do with Macaulay 2 or something. Okay, so, but I want to connect the abstract setup to our actual problem here that we're interested in. So let's go into the specific example. Let V be the space of m by n matrices So if you want to be a little fancier, you can say this is the exterior tensor product of an m-dimensional space and an n-dimensional space. And then that comes naturally with a group action that is GLM cross GLN, which on our matrices is acting by row and column operations, or it's like induced from the actions on the vector spaces of the tensor product, if you want to think of it that way. This is not the same thing as GLV. It's a subgroup of it, but everything I said here will go through just as well for products of general linear groups. The only difference is that here we'll have tensor products of Schur modules in like distinct sets of variables, and here we'll get products of Schur polynomials in distinct sets of variables. So writing this example is the most like notationally nice, but nothing theoretically becomes more complicated when we use this group action. Okay. Yeah, great. Then there's only a few G-stable varieties in the space of matrices. The only G-stable varieties are the so-called classical determinantal varieties, which I'll denote XK. And that's going to be the matrices of rank at most K. So, and right, this is just a fancy way of saying that the rank of a matrix is unchanged under arbitrary row and column operations, and it is the only statistic of a matrix, basically, that is unchanged under those operations. So, okay, so that means that we can try to compute the character of this thing equivariantly in terms of this G action. And if we do that, what do we get? I guess I'll try to squeeze it in here at the bottom. So we have a theorem, which I'm going to attribute to Dubélé, Rota, and Stein. Which says that the character of this determinantal variety is equal to the sum over all partitions with length at most K of S lambda X S lambda Y. In other words, it's exactly the left-hand side of this formula here. Okay. So this is a really beautiful result. I really like it. They proved it. They were doing invariant theory. The determinantal varieties show up in invariant theory. And to give characteristic-free proofs of the fundamental theorems of invariant theory for GL, they introduced something called a straightening law to like understand in sort of an equivariant way these varieties. And if you look at what their basis says, it gives you this form. You could also derive it from the standard monomial theory of Lakshmibai, Musili, Seshadri for the Grassmannian. You can think of classical determinantal varieties as affine patches of Schubert varieties in the Grassmannian. And then there's a standard monomial theory that gives you a basis that's nice and equivariant for the Grassmannian and the Schubert varieties in the Grassmannian. And it turns out that that descends to the affine patches to give you a nice bi-tableau basis, which is that same basis from Dubélé, Rota, and Stein that you can read this. At the end of the talk, if I have time, I'll mention a different proof in the last year that comes from me and my collaborators. Okay, are there any questions about that before I continue? All right, we're halfway through the talk and halfway through explaining the formula, so I think that's good. We talked about the left-hand side. Now let's talk about the right-hand side. So this was already mentioned, but the character of a coordinate ring specifically is special. It has more structure than just the arbitrary character of a random representation. It is actually the equivariant or the multigraded Hilbert series of the variety, of the embedded variety. And so in algebraic geometry and commutative algebra, you'll see people use that term a lot, and they've developed a lot of really nice techniques based around degeneration and things like that for computing Hilbert series. They've also proved nice theoretical results about the forms that these particular generating series have to have. And so the one that's going to be relevant to us today is called the Hilbert-Serre theorem. You'll never guess why it's called that. Which says that for, let's see, for any affine subvariety, I mean, really more generally for any like finitely generated module over a polynomial ring, but for any affine subscheme of our vector space in particular, the character of, or let's see, there exists a unique polynomial, which is called the K polynomial for the coordinate ring and some variables t1 through td. And this is an integer polynomial, not necessarily non-negative integer, such that the character for a coordinate ring of X is equal to the K polynomial divided by product I equals 1 to D of 1 minus Ti. Yes. Yeah. Mm-hmm. Yep, that's exactly where I'm going with this. Yep, very good. So yeah, so when Hilbert was originally studying Hilbert series and things like that, he understood it by through the Hilbert-Syzygy theorem, which tells you that every finitely generated module over a polynomial ring has a finite minimal free resolution that you can read off homological invariants like the Hilbert series from. And when you do that, you get this form. You get this nice formula that is, more compact and finite for what the Hilbert series is. This is the Euler characteristic of the minimal free resolution for our coordinate ring as a module over C adjoint B. Okay. And a nice fact, which we can see via elementary means, is that if we know that if G acts on X, then this thing is going to be a symmetric polynomial. This thing's also obviously a symmetric polynomial, the denominator here. And so the numerator must be symmetric as well. Or you could understand it by saying that you can make the terms in this resolution equivariant by doing constructions for like Tor groups and stuff, but it's not necessary to come to this conclusion. We get a second thing. So if we have a GL action on X, then the K polynomial also needs to have an equivariant expression. It's going to be some sum for lambda d lambda x s lambda. So now we're doubly happy as algebraic combinatorialists because given one variety with one group action, we have two sets of coefficients to find. And for classical determinantal varieties, this has been done, as you might be able to now guess from this formula, which looks very Hilbert-Serrish. So we have this theorem due to Lascaux. Actually, Lascaux's thesis in 1970 was that he computed equivariant minimal free resolutions for all the classical determinantal varieties. It's a really amazing result. And in particular, if you read off the terms of the resolution and read off the Euler characteristic, it turns out it's cancellation free. Every term that appears in the resolution appears exactly once. And you will see that the K polynomial for this thing in X variables and Y variables is exactly the right-hand side of this one. So the proof of this fact, the construction is really, really nice. It uses what people now call the Kempf-Lascaux-Weyman geometric technique. So they look at a resolution of singularities of the classical determinantal variety, and then they use some tricks with cohomology of vector bundles and Borel-Weygott, and they're able to compute the terms in the resolution explicitly, and you see that these are the Schur modules that pop out. Are there any questions about that?
this case, the resolution is there. Tensor problem.
Yes, I think that's right. It was not a question, but the answer is yes, that's a correct statement. Yeah, yes. So, okay, great. So now we have explained where the proof of this formula comes from. If you put together the Dubélé-Rota-Stein result, the Hilbert-Serre result, and the Lascaux result, those three things collectively give you this beautiful concrete formula. And I think that there is more to say about this formula. I think it would be great if people would seek out like combinatorial proofs and other things, but I think because these results were stated in more abstract language, a lot of the people who would like to give those proofs don't see this formula. So here you go. One more thing before I move on. There's actually, we can be triply happy as combinatorialists because there's another problem that we can look at besides these two, just given a variety with a group action on it. So the multi-degree of a variety of X is, I mean, you can describe it multiple ways. It has geometric significance, but algebraically, we can find it as the lowest degree part of the twisted K polynomial. K in 1 minus T1 to 1. So if we take our K polynomial, we do this funny variable substitution, then that gives us another interesting object to study, and the lowest degree part of it is the multi-degree, which geometrically tells you sort of about the intersection theory of X. It tells you if you intersect X with a hyperplane of the correct codimension, so that the intersection has a finite number of points, how many points? Or I guess that would be the degree, and then this is like some refinement that gives you a little bit more information. But we already know that if GL acts on X, then the K polynomial on the normal variables is symmetric. And so when we do the substitution, it must still be symmetric. And so that tells us that we have a twisted K polynomial that also has some expansion that we can try to understand. And this is especially interesting to do. Huh? In general, there's no theoretical guarantee that it needs to be positive. For the determinantal varieties, at least for the lowest degree component, they are positive. And in general, this has some alternation. So we have a theorem, and actually, reference request, I don't know exactly who to attribute this to. In the 80s and 90s, a ton of people worked on the multi-degrees of classical determinantal varieties. So like Abhyankar, Gorpade, Herzog-Trung, Stanley, Golden Green, like there were a whole bunch of people who were doing these different things. They gave a lot of like determinantal formulas and stuff like that. I don't know who is responsible for the equivariant expression. But the multi-degree of a classical determinantal variety is given by sum over lambda contained in m minus k times n minus k of s lambda in our x's times s lambda star transpose in the y's, where what's the relationship between lambda and lambda star? It's this. So you take an m minus k by n minus k rectangle, and then lambda and lambda star are like the complements in there. And so once again, we get a very nice multiplicity-free formula for the multi-degree. If you want to do the whole twisted K polynomial, the formula also exists, but I don't. I only know how to get it by chaining together a few formulas that were proven in greater generality. You get multiplicity, and I don't know like a super nice way of writing down what the formula is, but it is like, no. Any questions about that? No. Okay, great. So now in the last 10 minutes or so, I I guess we've done equivariant Hilbert series and determinantal varieties, but I haven't said anything about Grothendieck polynomials. And I also haven't said anything about my own work, so hopefully I can remedy both of those issues. So this whole story is pretty complete. I mean, I think there is still more to say about this formula because we don't have direct arguments. I think there's a lot of room to do like combinatorial stuff here, but we have the formula. And so in that sense, the theory is complete. All three of these questions have explicit answers. So let's look at a generalization where they don't. Matrix Schubert varieties are a generalization of classical determinantal varieties in several senses. So the important thing to know is that they live in the space of, now I'm going to say square matrices. You can actually do it in rectangular matrices, but it just makes the notation easier. And you can do it without loss of generality to work with square matrices. They're indexed by permutations. And these are determinantal varieties that are stable. They're the only varieties, or the only irreducible varieties in the space of matrices that are stable under the Borel group action by downward row operations and rightward column operations. And they're affine patches of Schubert varieties in the complete flag variety. And for many of the interpretations of classical determinantal varieties, these are like a natural generalization. I'm not going to write out the explicit definition, but basically they are defined by imposing rank conditions on various submatrices of your matrix, and like which submatrices and which rank conditions are all determined by the data of the permutation in some way that's not that complicated. Okay, so some Levy group by which I just mean a product of a bunch of GLs contained in our product of two GLs acting by row and column operations, acts on each matrix Schubert variety, on each X W. So which product you take depends on the descent positions of W and its inverse. Everything I'm going to say you could also try to do with the Borel group action. The problem is that the Borel group isn't reductive, so its representation theory isn't as nice. But you could still ask about it. And then for these questions, you'd be asking about like expansions into key polynomials or de Maizière atoms or things like that. But I want to stick to this story because that'll generalize this more nicely. We'll just have products of more and more sure polynomials. So now we have a theorem. Because for each of these matrix Schubert varieties, we have this product of GL actions. So we have these three questions that we can all ask. So here's a theorem due to Price, myself, and Alex Young from last year, which says that, so we gave a combinatorial rule for the coefficients in the first problem. So C lambda, really now it's two tuples of partitions that are for the row action and the column action for XW. So this is a non-cancellative combinatorial rule. It's based on RSK and it generalizes the Littlewood-Richardson rule. It's computationally effective. And we did this in a different way than the other work I've mentioned. We used what we're calling a Grosvenor crystal structure. So basically, Grosvenor bases for matrix Schubert varieties are already known, thanks to work of Knudsen and Miller. And using that, you can get what's called a basis of standard monomials for the coordinate ring of the matrix Schubert variety. And that corresponds geometrically to doing a degeneration of the variety, where you go from like some nice thing with a lot of symmetry to something that is more combinatorially nice because it's a union of coordinate subspaces. But when you do that, you destroy the symmetry. And our main result is that even though that action seems very destructive from the equivariant perspective, a combinatorial shadow of the symmetry that you had remains on the standard monomials in the form of what's called a crystal graph. So we show that there's this crystal structure on monomials and it descends really nicely to the standard monomials for matrix Schubert varieties. And actually, it turns out a lot of other varieties as well, like unions of matrix Schubert varieties or some other determinantal varieties defined by different types of rank conditions. Yeah, So long story short, we've solved that first problem in a pretty satisfactory way. Now, the third problem on the list also has a solution. Of what the C's look like. I mean, I can. It's not. I mean, I could tell you what the rule is. It's not super nice. It's in particular, it's not a rule in terms of Tableau. So you take non-negative integer matrices that correspond to the exponent vectors of standard monomials for the variety, which is a combinatorial condition based on avoiding certain antediagonals in the matrix. And then you say that it has to be highest weight with respect to the Levy action, which is some like parenthesis matching rule on the pairs of rows and pairs of columns. Yeah, and then it's the number of things that satisfy that rule. Yeah. So you can compute it with a computer, and we have programs to produce these things that are available online, and some examples in our paper with explicit coefficients. But yeah. So the third problem here also has a solution. It's a theorem. I'm gonna just say the names because there's too many of them. If you chain together formulas that are due to Fomin-Kirillov, Lennart, and Buch, Kresch, Tembakis, Young, by putting all of those together, you get like a combinatorial rule for D. Sorry, yeah, D lambda mu, I guess, XW. So this is also known. And part of that uses the result that from Knudsen and Miller which is that the K polynomial of a matrix Schubert variety in these X's and Y's is a Grothendieck polynomial in, I'm going to write it like this, and that the K polynomial, the twisted K polynomial, where we plug in 1 minus for all the variables, is what is also called a Grothendieck polynomial, somewhat confusingly. I'll denote it like this. And what I mean by this notation is, I think this is a Grothendieck polynomial friendly crowd. Is that true? Somewhat. Sorry. Well, you probably know that, or if you have studied this stuff, you might know that there's a formula in terms of RC graphs or pipe dreams for these things, where you take weights over like crossings in these certain diagrams. And this Grothendieck polynomial is what you get if the weight of a crossing in position ij is 1 minus xi and this is what you get if the weight of a crossing in position I and j is xi plus yj minus xi. So they're related in this way, and it turns out this Grothendieck polynomial is the one that is easier to understand equivariantly, or like in general. I think this is just a lot easier to understand if you work with the combinatorics of it. And so that's why we have the expansion for this. Like Fomin and Kirillov gave a Cauchy identity where they expand this Grothendieck into products of single Grothendieck polynomials, and then there are expansion formulas into Schuberts, and of the Schuberts into Schurs. But on the other hand, this one, if you try to expand it out, it's crazy. It's got a whole bunch of cancellation. It's very complicated. I don't know how to understand it at all. And so trying to do the analogous analysis to figure out this thing in the middle here, even though all three of these sets of coefficients seem related, I mean, like if you know one of them algebraically, you can compute the other. Coming up with combinatorial interpretations for them are three very different problems. And this one in the middle seems to be the hardest, as far as I can tell. It's at least the hardest in the sense that it's open and these two are not. Okay, so I guess I'm basically out of time. I want to say one more thing quick about progress towards this. So one way you could try to do it is you could try to generalize Lascaux's approach and just like literally figure out the minimal free resolutions. As far as I can tell, that's hard. Like you might be able to generalize his approach a little bit, but it doesn't seem like it's going to easily generalize to all matrix Schubert varieties. However, there are some nice like combinatorial signs of something happening, which we can maybe see in this original formula here. Notice that if I increment m, n, and k, then the indexing set here in the numerator stays the same. The actual partitions that appear change because they're bigger stabilizations, but there's like a bijection between the non-zero equivariant Betty numbers. And that bijection is given by a very simple operation, just like doing one additional stabilization on your partitions. So experimentally, we can compute these K polynomials for matrix Hilbert varieties, just like using Macaulay 2. And we've observed that you can do something similar to incrementing M, N, and K. You can compute the back stabilization of your permutation. So in the case where your permutation is bi-Grassmannian, then the matrix Hilbert variety is literally a classical determinantal variety, and then back stabilization is literally that operation of incrementing M, N, and K. In general, it's something that looks a little bit different. But we observe the same thing happening. At least when you stabilize enough times, we start to see a bijection between the non-zero Betty numbers that occur, which is basically the same thing. So there are signs that there is something interesting going on here. And we're starting to have a lot of combinatorial techniques that are lying around for all the different sides. And so hopefully we'll be able to make some sort of breakthrough at some point and start to understand those numbers as well. And I guess that's all I've got. Thank you very much for your attention. Yes.
So you can't, I mean, obviously this won't work, otherwise you would have said it, but you can't just multiply the character by the denominator. It's like expand out the.
Yeah, well, I mean, I can't even do that for classical determinantal varieties. I mean, like I can. Well, it's not.
That the left-hand side by the denominator, right-hand side. Don't I know that the numerator looks something like that?
Yeah, well, but it's not positive, because if I take this and I expand it out, then I have a big alternating thing, and then I'm doing Littlewood-Richardson rules, and so I get a pretty complicated. No. I mean, because you'll see like a whole bunch of other shapes will appear, and on all of them, the coefficient turns out to be 0 from the alternating sums, except on these few where it is something very simple. Yeah, so explaining that cancellation, I don't know how to do even here, except when K. Yeah.
And that is probably not trivial at all.
No, I didn't know how to do it, and then Liam had some good ideas, and it was like, oh, okay, I guess this is doable. Yeah. No, finding a vector bundle is fine because you can use. I mean, there are a few ways you could try to think about it. I think what you would do is you would take like the Bott-Samuelson resolution, one of those for the Hilbert variety, and then you would try to look at like affine patches or like some analog of that. So yeah, the problem is that like the way that technique works is you do your resolution of singularities. In the resolved thing, it's nice, and you know that you can just use a Kazul complex to get the resolution, but then you push it down. And when you push it down through their machinery, you get these like sheaf cohomology groups that are twisting your like Kazul complex terms, and you have to be able to compute those. And the tricky thing about that technique is that you have to get lucky. Like usually we can't compute just like random sheaf cohomology groups. And well, I mean, honestly, if you could do it for dominant permutations, I would still think that was interesting. But yeah, in general, it's not. Yeah, I mean, I think basically any case, I feel like you can probably make it work for Grassmannian permutations. That's one of those things that's like on my to-do list, but I haven't gotten around to it. But for like more general matrix Hilbert varieties, I think the problem is that you can compute the like resolved thing, but then when you push down, you get sheaf cohomology groups that aren't exactly the ones that Borel-Bott can do, which is what happens when you do it for classical determinantal varieties.
Back to the set.
Yeah.
So, these are Schur's as well, right?
Yeah, if it's an anti-dominant composition, yeah.
So if I was to have the non-symmetric Cauchy kernel at the denominator, is there a version of this identity coming from like the B module story, which has key polynomial, sine sum of product of these, and the non-symmetric Cauchy kernel in the denominator?
Oh, in
Like this particular.
In the
transaction.
denominator. So what you can do is you can say, so this identity, if we do it for k being the minimum of m and n, is just telling you like, how does the coordinate ring of this look as a representation, and then writing it rationally. Where like on the one hand, you can take this as a generating series over monomials of their weights, which are non-negative integer matrices. On the other hand, you can compute it equivariantly. You can also look at C where it's like, upper triangular matrices.
Right.
And then you'll have, on the one hand, it's a generating series for upper triangular non-negative integer matrices. And on the other hand, the character of this is equal to a sum over all compositions of like key in the x's atom of, I guess, it's like if you do a right atom or if you twist by W naught, that's all I mean by that, then you get this expression. And you can also, there's a recent paper that lets you understand this representation theoretically using like de Maizière modules and Van Callen modules. And they explain how like you're taking the symmetric algebra on this space and you're like doing really the same kind of representation theory. It's just more complicated. And they also explain how that generalizes for other partition shapes here. It's Fagan, I don't know how to pronounce his name, sorry. And like and then two collaborators like Makadoshki and I forget the other person's name, but it's called Cauchy identities for staircase matrices. And it's on the archive, yeah. Yes, so that is known. What I don't know I don't think they have the corresponding thing up here. And I'm not sure that you have, like, because the representation theory of the Borel group isn't as good, I'm not sure that you have like a guarantee that something like this has to exist. It might exist, and I mean, you can just mess around in Macaulay 2 and try. But it can be a little messy. It's kind of funny because if you do this specific case and you compute the multi-degree, then I believe what you get is the Cauchy identity for Hilbert polynomials appearing. And so it seems like maybe when you want to ask the analog of this question for a situation like this, you should be using Hilbert polynomials and not key polynomials. And this is another like set of things that I'm very interested in trying to understand. So if you have thoughts, we should talk. Yeah.
No questions? Let's thank Peter again.
Okay.
Okay.